Okay. Here I have it's a capacitor. Anytime you have two metal surfaces facing one another, you have a capacitor. There are other ways to form a capacitor. I've got one here. What happens with a capacitor is if you can move charge off of one capacitor onto the other, then if the capacitor plates are one plate, I'm going to call this a plate, I'm going to call this a plate. If you can move charge from this plate to this plate, then that leaves an equal and opposite charge on this plate, and whatever charge you move will be on this plate. For example, if I move things seem to be migrating. If I move a nanocoulomb of negative charge from this plate to this plate, that leaves me a nanocoulomb of positive charge on this plate and a nanocoulomb of negative charge on this plate. Now, nanocoulomb would be quite a bit of charge to move off of these plates. Okay, a nanocoulomb of charge would make these things pretty strong static electricity sources. Okay, now I've got a generator here. If I crank this generator, and if the polarity is if the polarity agrees with the colors of these wires, then what I'm doing is I'm moving electrons from here over to here, making this positively charged. And that was wrong. Move electrons from here to here, which makes this positively charged and this negatively charged. Okay, moving electrons away from the positive toward the negative. Now, electrons being negatively charged don't really want to leave a positively charged terminal, which is why you need to give them some persuasion. Well, with this generator, I'm only producing a few volts. The static electricity you get if you get a spark, you can shuffle your feet across the floor and try to touch something metallic, you get a little shock. And if you do it right, you can get a pretty good shock. Okay. The voltage there is in the thousands or even tens of thousands of volts. So I'm not going to get much from something that generates at most in the order of 10 volts. So we're not going to be able to observe the effects of this capacitor. So I'm going to disassemble this capacitor and put it back with its buddies and let it get back to its original purpose. Okay, this capacitor is not a parallel plate capacitor. What we saw before had two parallel plates. This capacitor separates charge, but at a molecular level in a way I don't understand. I don't think I have enough documentation. If I start cranking is fairly, you can feel a good bit of mechanical resistance, not to be confused with electrical resistance, in the handle. But I'm no longer feeling that. I'm feeling less and less mechanical resistance. Now what I'm doing is I'm transferring charge. Again, if I've got the polarity here right, and I haven't checked to see, I'm transferring electrons from here to here. And at the molecular level, somehow within the material, within this container, I've now got positive charges in one place, negative charges in another, in a way that the positive charges articulate with this terminal and the negative charges with this terminal. Now, I can do that again, and the same thing happens. Now, for some reason, we'll maybe talk about, the cranking gets easier and easier and easier. Well, when the cranking gets really easy, that means unless I crank faster, in which case it gets harder again. That means that I've separated about as much charge as I'm going to separate. Okay? So now, at the negative terminal, the black terminal, I've got excess positive charge. At the red terminal, I've got, let's say excess positive. The black terminal, I've got excess negative charge. At the red terminal, I've got excess positive charge. If I allow the current to flow naturally, then the electrons in the vicinity of the excess will be repelling each other, as will the positive charges. Positive charges turn out not to be particularly mobile. And what's going to happen is you're going to have a migration of negative charge from the black terminal to the red terminal. Now, if I let go of the generator, well, that's what's happening. And as the negative charge drifts along the path and into the generator and back to here, there's a current in the coil within this generator which interacts with the magnetic field to exert a force on the coil. And we've seen how a current can exert a force on a coil. Now, as there's less and less negative charge here and less positive over here, things slow down. One clarification, when I say the electrons over here want to go over here, yeah, they do tend to go over here, but they don't get very far. All the electrons that I separated here are equivalent to the number of free electrons in a fairly short segment of wire. So what you get is a repulsion of the electrons at this terminal by the negative charge here that creates an electric field within the wire and causes the charge carriers, in this case electrons, to slowly drift in the direction from the negative to the positive. That would incidentally be a negative current. It's a negative charge that's drifting. The drift is actually quite slow, maybe just a couple of millimeters per second, if that. So we don't really think of the electrons here ending up here. We think of electrons within the wire being pushed away from here, and the electrons at this end of the wire being pushed into the negative, into the positive terminal to neutralize some of the positive charges that were left behind when the electrons migrated away from the positive terminal.